y's and the x's.
Good. So we're going to basically kind of move things around. So all my x's will come together, all my y's will come together. Let me write my new equation. X squared minus 4x plus y squared minus 4y. And what should I do with the 4? Subtract it and get it to the other side. So don't forget about that 4, because if you forgot about it, you might have gotten the wrong answer. Okay, now we're here. What do I do next? Okay, we're going to put in our little blank spaces. And figure out what goes there. Completing the square, yeah. So, okay, what is going to go into this blank spot? Good, Emily, we got 4. So as a quick reminder, we divide this by 2 to get -2. Then I'm going to square that number to the power of 2. I got +4. But since I put it there, where else do I have to do that? On the other side. So +4 over here as well. Okay, same thing here. What's going to go in my other blank spot? Also 4. Same thing, divide this by 2, you get -2, square it, you get +4, and we do it on the other side as well. So now I've got this situation. What do I do next? We can combine on the right side and factor out on the left side. So on the right side, -4 plus 4 is 0. Add another 4 to that, you get 4. On the left side, I get x, what goes in here? I don't want to give it away. Good, -2, the magic number, squared. Same thing here. The magic number goes here, squared. And now we have our final equation. So how do I go from there to find my radius? Thanks, it's a shirt. So which of these numbers is representing my radius? The 4. But you got to remember to take the square root of that, because this right here, that's r squared. Oops. So if r squared equals 4, then r all on its own, what does it equal? What's my answer? Good. R is 2. So A. So it is kind of a lengthy process, and I just wanted to review it one more time. Does anyone have any questions on any part of that, any steps of that whole process? Two of the biggest common mistakes is to get this answer and then think it's going to be 4. So make sure that you always got to take the square root of that number. And let's see. And then another big mistake is just to forget to add it to both sides. So whatever you add on the left side, you have to remember to balance it out and add it also on the right side. All right, so any questions at all? Going once? Going twice? All right, cool. So today, like I mentioned yesterday, we're kind of covering 2 like smaller sort of topics. There's not that many questions on these on the test, but there are a couple, so we do have to make sure we go through it and understand. Now, I am going to give you a fair warning. These 2 topics are a little bit, can get confusing, I guess. So I'm going to do my best to explain it as best as I can, because for me, like it was confusing to learn it when I was in school. So I just want to make sure that that I'm doing my best to explain it. So make sure if you have any problems, any confusions, anytime that you just need me to explain it again, let me know in the chat or out loud. Okay, so we got a circle. We got a pizza, actually. And let's just say you take your pizza and you split it into 8 slices. And then you arrange the slices in this way, okay? So let's just analyze what's happening in this situation. What kind of shape is created when you put everything like this? It's not a trapezoid. It's actually something more specific. It's not a rhombus, because remember, rhombus have equal sides. So think out a little bit, a little less specific than that. There you go. This is a parallelogram. It creates a parallelogram if you do that. And let's talk about parallelograms for 1 second. So the area of a parallelogram is pretty simple. It's just base times height. It's kind of like a rectangle, base times height. So let's kind of look at this parallelogram and think about what would be the base of it and what would be the height of it. And the way to kind of figure that out, I'm just going to highlight some things on my pizza. So think of the crust. Let's see, let's pick a good color that's going to stand out. So I have crusts all over here, over here, over here, over here. How many crusts are on the bottom, the base? 4, right? 4 crusts. How much of the circle is 4 crusts? 1/2, right? We agree? So half of this circle, half of it can be, you can kind of see that that's on the bottom, and then the other half of it would be on top. Make sense? Any questions on that real quick? Okay. Now, the crust of a parallelogram, the crust, if I take the full crust, what would that be? Of a circle, I mean. The whole crust is the what? If I go all the way around just the crust, what is that called on a circle? It's the circumference, right? So really quickly, just remind me, circumference is what? What's the little formula we have for circumference? 2 pi r. Well, if I have, let me just move this over. If I only have a half of the circle, so just the blue part of the circle, what would I need to do to the circumference? Why did I put p? That should be a pi. We would divide it by 2, right? So the circumference of the whole circle is 2 pi r, but the circumference of the half of the circle, so half of the circumference, would just be pi r, because I would just have to divide it by 2. Does anyone have any questions on that idea? So 2 pi r is the whole circle, just pi r is half of the circle. Well, sorry, I keep moving this around. Okay. Well, since I've got all these crusts lined up over here, that's half of the circle. So the length of the base would be pi r. Does half of a circle count as an arc? Definitely. Yeah, definitely. That's a very specific type of arc because it's a semicircle. But yeah, it's still an arc. So since I have half of the circle represented right here, I have 4 crusts, 1, 2, 3, 4. That corresponds to half of the radius. Half of the crusts are half of the radius. Questions on that? I'm taking it real slow because I just want to make sure we understand. Okay. So the area of this parallelogram is going to be base times height. So we know the base is pi r, but what's the height going to be? Let's talk about height. So here's the purple section right here. Now, if I go and I color that into my actual circle, what is that representing? The radius. Now, it's not exactly the height, because if you really think about it, the height is technically this distance right here. That would be the height. So we're kind of like approximating it. We're not going to be exactly getting the right answer, but the height is going to be pretty close in value to the radius, because I know that this purple section right here is the radius. So the height is approximately r. Same thing with the base. Think about what's happening in the base. I'm going kind of up and down, up and down, up and down, like a kind of like a wave rather than going straight across. So the base isn't going to be exactly pi r, it's going to be approximately pi r. So the base is approximately half of the radius, or sorry, the base is approximately half of the circumference, and the height is approximately the same as the radius. So if I plug that into the area formula, I would get pi r times r. What does that leave me with? What do I get? I get pi r squared. Area equals pi r squared. So the idea here is that you can approximately get the same area, the same answer for area, by using this, what we call like an approximation, by turning it into a parallelogram. You can get pretty much the same answer. You end up with the same formula. Kind of a weird topic. Like I said, like I mentioned at the beginning, these are, I left these two topics for last because they're kind of like okay, and what, like, why is this useful? But it's just kind of an interesting relationship to notice about circles. So at this point, does anyone have any questions? Yep, I was the same when I was in, I was like, why am I learning this? What does this matter? But so does anyone have any questions so far? Okay. So I want to kind of show this a different way. So I also have a GeoGebra link, and I want everyone to go ahead and click on it. It is my favorite place, honestly. I really like it because it is really good at showing you different things that are hard. It's hard to see it if you don't have it in front of you. So go through it, click on the little boxes as you go. Slide it, do what it's telling you to do. All right, so click through it just one more time. Go through the whole thing one more time. Go from the beginning. And let me know if there's any questions at this point. Any questions? All right. So click on it, take like 10 more seconds, and then head back to Zoom. Normally the formula is just pi r squared. Area equals pi r squared. So just again, it's kind of silly. I completely agree. It's a little bit silly, but it's interesting to see how you can turn a circle into a parallelogram essentially, and then use what we know about parallelograms to find the area of a circle. But let's just look at a interesting situation. Can I get a volunteer to read this problem? What's Evelyn doing?
That
Sorry.
literally has my name on it. No, I'm reading
No,
from the.
Tyrone. Evelyn divides
No.
a circle and
Oh my
rearranges the
gosh.
pieces to make a shape that resembles a parallelogram. She then divides the circle into more pieces and rearranges them into a shape that resembles a parallelogram. She thinks that the area of the new parallelogram will be closer to the area of the circle. Is she correct? Explain.
All right, so she divided it once like this, and then she decided to divide the circle into more pieces. So let me kind of see what that would look like. So basically what she's saying is, okay, now I want to like keep cutting it into smaller and smaller slices. So instead of 8 slices in her pizza, she wants to have 16 slices in her pizza. And then she wants to do the same thing, but this time, what's going to happen with the triangles when she lines them up? When she does this the second time around, so now her slices are smaller, what's going to happen? What's true about the new triangles? Okay, so they're half the width, yeah, of the other ones. Well, let's think about it. Is it going to be shorter? Longer? You think it might be longer? That's okay. No, we're trying to understand what's happening, right? It's going to end up the same. But the difference is that when she lines them all up, they're going to be skinnier, right? So if you kind of think about it this way, it's still going to make the same parallelogram. It's just that the pieces of the parallelogram are going to be smaller and therefore kind of closer like this. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2 more, 11, 12. Okay, so let me make this just a little bit bigger so it matches a little better. Something like that. Obviously, I'm just sketching it out, but it's going to look something more like this. Now let's think about this situation. Does the actual length of the base change at all? No, right? This is still pi r. Does the height of it change at all? Tyrone says yes. I want to ask why, because I kind of understand why you might say yes, and it's important. Not sure? You just felt like saying yes? Okay. Well, let's think about this. Think about, we have this triangle over here, which is a little bit wider. And let me take this triangle over here, which is a little bit skinnier, right? Which of these, it's kind of hard to explain, but if the radius is the height of the triangle, which triangle has side lengths that are kind of closer to the radius? The skinnier one, right? So the skinnier triangle is actually closer to the radius. Remember what we said, that it's an approximation. It's not going to be exact. Not going to be exact, but the skinnier triangle gets closer and closer and closer to the actual radius. The fatter, the wider the triangle is, the less of, like, the further away it's actually going to be from the radius, because the radius would be the height of the triangle. So the skinnier you get, the closer and closer you get to the actual height. Now, I know that's a little bit weird to understand, so let me show you a picture. Yes, Perla, that is exactly what Perla just said in the chat is 100% correct. Okay, if you divide it, the more pieces of pie, the more pieces or slices of pizza that you have, the closer you get to actually getting the actual number for the area. So let me show you a picture. So take a look at this example. Now take a look at this. Look at the circles below, which have been subdivided into different amounts of triangles. What do you guys notice? As you divide it more and more and more, what happens? So here's my first one. It makes this type of shape. Here's my last one. Yeah, so look at what Perla just said. As we go down, the shape gets closer and closer and closer to being a rectangle. And a rectangle would be the most accurate measurement, right? Because then the height is exactly the same height and the base is exactly the same base. The problem with a parallelogram is that the height is this. And so you don't actually get a good measurement when you're using the measurement of the side length. But on a rectangle, the height is the same as the side length. So the more subdivisions you have, the more triangles that you divide it into, the more slices of your pizza, the closer and closer you get to being a rectangle, and the closer and closer you get to having an accurate measurement for the area. So I'm going to go ahead and write that down. So we're going to write this down a little bit more mathematically, but that's okay. So n is the number of triangles. Okay. So as n approaches infinity, what does that mean? What does it mean to approach infinity? If I'm a number and I'm getting closer and closer to infinity, I'm getting bigger and bigger and bigger, right? So as n approaches infinity, I'm going to write as it gets bigger and bigger, or as it increases, the approximation is going to get closer and closer to, what's the area of a circle? Pi r squared. So as n gets closer to infinity, the approximation gets closer to pi r squared. Questions on that idea? Okay, so make sure you write it down, and then I'm going to show you guys another GeoGebra, but this time I'm going to keep it on my screen. Okay, I'm just pulling it up. Give me one moment. And then we can go through it together. It's loading very slowly as usual. Okay. Sorry, my GeoGebra is glitching slightly. It's taking forever. Okay, there we go. All right, so I'm going to share my screen, and then we can kind of see another example, because it kind of helps to see it, like to see actual numbers and see what I mean. Because right now I've just been telling you. But now let's take a look. So here's just a circle. I'm going to make the radius 3. So when the circle has a radius of 3 units, the area should be 28.27. 28.27. Now, I'm going to bring this down. This is n. This is the number of triangles. So think of each section of like this. This is what, an octagon? Think of it like it's slicing it into that many pieces. So this is 8 pieces, okay? When it's in 8 segments, 8 pieces, if I try to calculate the area, I would get 25.46. So is that exactly the same, or is it still pretty far away from the actual area? It's kind of far, right? 25.46 it's close to the actual area, but it's pretty far still. Now let me increase the number of triangles. Let's go to 17. 28.27 is what I want to get. Right now I'm at 27.63. So what happens? It's getting a little bit closer, right? Now I'm going to do it a couple more times. Let's go to 25. Now I have 25. Think of these as slices, 25 little tiny slices. If the actual area is 28.27, I'm getting closer and closer and closer. And I can have this go as far as I can. And as I get closer, or as I add more triangles, the number gets closer and closer to the actual area. If I go the other way, it gets further and further. Okay. So that's kind of how this works. That's kind of how this works. Do I have questions on this? All right. Okay, now back to it. Let's do a couple problems. That's it, by the way. That's the whole topic of this mini topic. So now we can do a couple practice problems, and then you'll see what it kind of looks like if they ask you on a test. Nope, we're not really calculating anything at all. It's just understanding how it works. All right, Tyrone, you can go ahead and read this one.
Yay. The circle with the radius r units is divided into congruent sectors to create the shape below. For estimation purposes, which shape formed by the sectors is considered to be a parallelogram? Which statement is true?
All right, so take a look. This is purely like definition. So take a look, go back to what we wrote down about the definition and see if you can correctly answer this question. All right, I have 2 answers in the chat. Remember, this is just definition question. There's no math involved. This just, if you wrote it down 2 slides ago, you should be able to get this one. Take 30 more seconds. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. Most people got it right. One person got it flipped, kind of. So let's look back at it. I wrote it down right here. So you could have looked at your notes, but something tells me that the person who got it wrong and the 2 people who didn't answer didn't write down their notes. Because like this is a very easy, very easy problem. But only 3 people got it right out of everybody here. So if you don't have this in your notebook, write it down right now. The length, the base is pi r. The height is r. Pretty simple. Did I have any questions? No, I did not have any questions. But do I have any questions now? Okay. So one more time, answer choice A is correct. The height would be r units and the base would be pi r units. And if you get this question wrong on a test, I'm gonna be very upset with you. Because again, there's no math involved. There was nothing involved except did you write down the actual definition or did you not write down the actual definition? Any questions on this one? Okay, one more. Who would like to read this one? Maybe Jalen?
Miss Lopez.
Absolutely not.
Wow.
A circular radius r is divided into n equal sections. In the figure below, n equals 8. The area of the circle can be estimated by thinking of each pie-shaped piece as a triangle with base b and height h. The more sections n the circle is divided into, the closer the approximation of the area. As n gets larger, which statement must be true?
Thank you. Perfect. All right. So think about this one. This one's definitely a little bit more challenging, but I want everyone to really think about it, read each problem carefully, and see if you can get the right response.
Miss, what does H mean?
Height. They say it right here, base and height.
Oh, I'm so dumb. I'm sorry.
It's okay. We are drinking tea today, yes. All right, almost everyone has voted, so 10 more seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Yeah, like I expected, this one was a little tougher. So we were pretty split in general, but then we were split mostly between A and B. Now let's take a look. Let me explain this one more time a slightly different way, because I think some of you guys just need to visualize it a little bit better. This is the radius, right? So on a triangle, let me make it a little bit bigger just so we can kind of see it more clearly. On this triangle, I have the radius right here, and then the height would be this red line, okay? Now, this is, let's say we split this triangle in half. Let's say we cut it into half and we make it much, much thinner. Again, this is the radius, and then this is the height of the triangle. I'm going to do it one more time. I'm going to make it even thinner than that. Make it super, super thin. Okay. And again, here's my radius. And then this is the height. As it gets thinner and thinner and thinner and thinner, what's getting closer and closer and closer together? What gets closer and closer together? The height gets closer to the radius, yeah. Look how far away they are over here. They're very, the height is here, the radius is pretty far away, right? As the triangle gets thinner and thinner, the distance between the radius and the height gets closer and closer together. So as it gets smaller and smaller, the height is going to get closer and closer to the radius. I'm going to say that one more time. And I'm going to do it even thinner if I possibly can. When you've got this tiny little triangle that's really, really skinny, it's hard to draw it, but I'm trying to do my best. The skinnier the triangle is, the closer the height is going to be to the radius. So as n approaches infinity, the height of the triangle is going to get closer to the value of the radius. So C and D are out, A and B are still in. Questions on that? As the number of triangles gets bigger, the height of each triangle is going to get closer to the radius. Okay, now the second part of that also matters because now they're saying B times N. Well, B is the base. B is the base. So the number, let me do it this way. B is the base. So here's one base. And if I go all the way around the circle, how many bases are there? How many? 8, right? How many triangles are there? 8 triangles, 8 bases, all the way around. So B times N just means the number of bases, or not the number of bases, the length of each base times the number of bases, or the number of triangles. So if I have 8 triangles going all the way around, what is that distance called? All the way around. Not halfway, but all the way around. What is that called? That's the circumference. So B times the number of triangles would be the circumference. And what's going to happen is as you add triangles, you're going to get closer and closer and closer to the circumference. So which of these is circumference? Pi r or 2 pi r? Which one has it right? B has it right, 2 pi r. The circumference is 2 pi r. So this one was kind of challenging because it doesn't really match with what we were doing before. Because kind of what they're saying in this problem, they're like, okay, let's line up all the triangles this way. There's 8, 1, 2, 3, 4, 5, 6, 7, 8. When you line them up this way, that's the full circumference. That's 2 pi r. If you stack them up one on, every other, then that's half of the circumference. So this question was tricky. I definitely wanted to explain it a little bit better. So any questions on this one? All right, well, that's it for this. That's it for this mini topic. So kind of weird, kind of different, but there'll be like 1 or 2 problems about it on your test. Now let's move on to something else. Equally weird, but also equally not as important on your test. Take a moment, let me copy this link. Click on the link, and I'll give you guys about 4 minutes on this one. Interesting, yeah. Take about 30 more seconds. Jalen, here's the link. All right, 10 more seconds. Start heading back to the Zoom. And 5, 4, 3, 2, and 1. All right. So what did you guys notice? What was this, in your own words, let's kind of describe what was happening in this GeoGebra. What were they doing? They were wrapping it around the circle. So you take the radius of the circle and you kind of see how many times can you wrap that radius around the whole circle. Yeah, exactly. That's a really good way of thinking about it. Okay, so when you do that, when you do that, you end up with these angle measurements. These are measurements of angles. And this angle, we call it 1 radian. So where it says rad, that's short for radian. So when you see the word rad, that's a radian. We call them radians. So in your own words, what exactly is a radian? This is 1 radian. How do I get 1 radian? What did they do here? They wrap the radius 1 time. Exactly. So a radian is the angle formed by wrapping the radius around the circumference 1 time. So it's like an arc. It literally is an arc. The length of the arc is the same as the length of the radius. So I'll kind of note that down. This blue arc has the same length as the radius. All of those arcs have the same length as the radius. So a radian is the angle that you form by wrapping the radius around the circumference 1 time. That's 1 radian. So now the question is, how many radians fit in a full circle? And you might want to go back to the GeoGebra because it tells you at the end. I don't have it on the screen here. Jalen has it, 6.28. So this little piece left over, oh, that's a bad color. The little piece that's left over after you get 6, that's 0.28. So going all the way around the circle, you get 6.28 radians. Okay, so if you do the circumference divided by the radius, you should get that number. But let's think about what that number is. 6.28. What's that number divided by 2? Oh, 3.14. What's that number? Oh, that's pi. Interesting. So the amount of radians that fit all the way around the circle, it's 2 pi radians. That's how many fit. 2 pi. 2 times 3.14. Crazy, right? Okay, so radians are kind of weird. They're a little bit strange, but it's very interesting where they come from. This is exactly where they come from. But at the end of the day, a radian is just an angle that is part of the circle. Do I have any questions so far? Okay, so let's think about this for a second. We already said how many radians are in a full circle? 6.28. And with that number, we always just want to say 2 pi. In my head, I know that 2 times pi is 6.28, but when I write it down, I'm going to always write 2 pi. How many degrees is a full circle? 360. So 360 degrees is equal to 2 pi radians. Now, how about the other one? How many radians would be in a semicircle? Half of a circle. That's 180 degrees, but how many radians would that be? Just 1 pi. So a full circle is 2 pi radians. Half of a circle is just pi. Okay, so what happens is think about like, oh, and what about a quarter? That's a good question. Let me just stick it in right here. How many degrees is a quarter of a circle? $90. What's half of pi? Yeah, half pi radians. And so forth. Yep. Okay, so think about it this way. You know how when you measure different things like temperature can be Fahrenheit, it could be Celsius. If you're measuring length, you have feet, inches, meters. There's different ways to measure feet or length. If I'm drinking a cup out of a cup, this could be milliliters, ounces, cups, pints. There's a lot of different ways to measure this. It's kind of the same thing. With angle measurements, you can measure it using degree measurements, and we know how to use those already, or you can measure angles using radians. So it's like 2 different units, okay, to measure the same exact thing. So think of radians and degrees, kind of similar to how you can have feet and meters, or miles and kilometers, different measurements like that. So what's going to happen is we can convert from one to the other. We kind of did it on this page, but these numbers are pretty easy, right? 360 is just a full circle, 180, 90. But what if I have different numbers like 22 degrees or 13 degrees, numbers that are just not as easy to work with? Well, let's think about it for a moment. So take a look at the circle below. The highlighted angle measures 1 radian. What is the measure of the angle in degrees? Answer and express your answer in terms of pi. Okay, so we know a couple things about this circle. The length of the arc is 4 units. The length of the radius is 4 units. And we know that the angle is 1 radian, but I don't know how many degrees that is. Okay, so I'm just going to call this theta for now, because I'm trying to figure out, I know how much it is using radians, but I don't know how much it is using degrees. Well, remember, we can always figure it out using our proportion. So if I'm looking for the measurement of the angle, that's going to be theta over what? Remember, we have our proportion. I want to know how much is that angle measuring. So out of the whole circle, theta out of 360 would be equal to, we know the arc is 4 units, and that's 4 out of what? Two pi r, the circumference. Oops. All right. So really quickly, I can do a little bit of cross multiplication. So 2 pi r theta is equal to 360 times 4. What would that be?
$1,440.
1,440. Oh, I forgot that we know the radius. We know that the radius is 4. So let me fill that in really quickly. So I can actually multiply that. So that's 8 pi theta equals 1440. And I want to know the measurement of theta, so what should I divide on both sides? Divide by 8 pi. What's 1440 divided by 8? You sure? 180. So this is 180 over pi. And that's the amount of degrees. So I'm going to write degrees. So let's kind of summarize what we just found out. We just realized that, oh my goodness, it doesn't want to move. Hold on. There we go. So with all that math that we just did, we just realized, we just showed how 1 radian is equal to 180 over pi degrees. Now on the previous slide, what did we just say? 180 degrees is pi radians. So does anyone notice a pattern? One radian is 180 divided by pi degrees. Pi radians is 180 degrees. What's the number that seems to be popping up a lot? Pi and 180. And those two numbers are the magic numbers because there's a way to be able to convert back and forth really, really easily. And let me show you what that is. Let me skip to this slide. We can convert back and forth using a fraction very, very easily. If you want to go from radians to degrees, you multiply times 180 over pi. If you want to go the opposite way, from degrees to radians, you multiply times pi over 180. So right now, go ahead and write this in your notebooks. This is going to save your life, trust me. Write it down. I know that it's a little strange. I know it's a little different. I know it's a little weird, but it is really important, believe it or not. So go ahead and write it down. All right. Anyone still writing? Cool. So let's do a couple of quick little problems. It's not too bad. We're going to convert the following radian measurements to degree measurements. Okay? So again, I'm going to write it down. I'm going to write the conversion. We just wrote it down over here. So if I want to go from radians to degrees, I do 180 divided by pi. So if I have 4 radians, I'm going to multiply 4 times 180 over pi. What's 4 times 180?
$45.
4 times 180?
Oh, I did divide it. My bad.
It's okay. 720. So this is 720 over pi degrees. Now, obviously this fraction's a little bit like weird, right? You can always get the answer, the actual final answer, just divide by 3.14. What's 720 divided by 3.14? Approximately.
229.229.
So about 229 degrees. So this is my exact answer. I'm going to leave it in terms of pi, but it's approximately 229 degrees. Let's do the next one. 3 over 2 radians times 180 over pi. What's 3 times 180? $540. So this is 540 over 2 pi. Well, we can just simplify this by dividing. What's 540 divided by 2?
Miss, I got 270.
Yeah.
No,
200.
wait, what?
You're right.
I'm confused now. Wait. Let me just go back.
Okay. So
Oh,
I
never mind.
I multiplied straight across, and then I just simplified by dividing. 540 divided by 2 gave me 270. So this is 270 over pi degrees. How much is that approximately? Good. When you actually divide by 3.14, it's approximately 86 degrees. I'm going to round up, 86 degrees. See, do you guys see the pattern? It's a little bit, you just have to remember which direction you're going in. You got to remember the conversion. Once you memorize that little tiny detail, you just plug things in and solve. Now, pi radians. Pi times 180 over pi. What do I get? Careful, how do we multiply that pi that's on the outside gets multiplied by the numerator, not the denominator. Good. 180 pi over pi. Well, what happens there? It gets canceled out, yeah. So you end up with 180 degrees. But we already knew that, right? We already knew that. 180 degrees is pi radians. So what's 2 pi radians? Yeah, 360. Now let's see why that works out. 2 pi times 180 over pi. That's 360 pi over pi. They cancel out. I'm left with 360 degrees. So to convert from radians to degrees, we just do 180 over pi. You just multiply by that number and you get your answer. And we have the exact answer, you leave pi where it is. If you want to know the approximate answer, you can divide by pi. Questions? All right, now let's go the other way around. Oh wait, I have a couple more, sorry. I have a couple more, but honestly, the test does not even go this deep into detail, so we're not going to do it. Not necessary. But let's go the other way around. So now I want to go from degrees to radians. So instead of 180 over pi, you flip. It's pi over 180. So 40 degrees. That's going to be 40 times pi over 180. What do I get? $40 pi over 180. Can I simplify that fraction, 40 over 180? 2 over, not 2 over 90, 2 over 9. So this is 2 over 9 pi radians. Or you can leave it as 2 pi over 9 radians. Let's try the other one. 80 degrees. 80 times pi over 180. This is 80 pi over 180. What's 80 over 180? Simplified. Good, Emily. 4 over 9. So this is 4 over 9 pi radians. Or you can write it as 4 pi over 9 radians. I'll say it again. I understand this is weird. This is different. It's kind of like, why am I doing this? Doesn't make sense. I'll say this, long story short, you'll see this again probably in pre-calculus. So you don't have to worry about it again for a while. But once it comes back, you're going to be thankful you learned it simplified the first time because it gets harder than that in pre-calc. But even if it doesn't like sit right with you, even if you don't really like get why you have to do this and you're like, Miss Lopez, what, like, why are you making my life harder right now? Just as long as you know how to do it, then do it right. And that's all I ask. Okay? Just do it right. We have the little formula. It's not that hard. It's annoying, but it's not that hard. So 100 times pi over 180. What do I get? What do I get? What do I get? 100 pi over 180. Simplify it. 5 over 9. 5 over 9 pi radians. Or 5 pi over 9 radians. Try the last one on your own. Try it on your own. Take 30 seconds. All right, 10 more seconds. Good, Perla. You got it. All right, so 12 times pi over 180. That's 12 pi over 180. Simplifying that number, 12 over 180, you can go slowly. I had to take a moment with this one. So 12 over 180 is the same as 6 over 90. Keep going down. That's 3 over 45. And what's 45 divided by 3? 15. So it's just pi over 15. Or you could write that as 1 over 15 pi. All right. So yeah, I mean, I don't know. I agree. I hated learning these when I was your age too. I totally understand. It is kind of a headache. But if you go on to much more complicated math in the future, it will come back. And we're just going to have to deal with it when it does. So did I like my geo? I loved my math teacher when I took geometry. It was my favorite class. Oh, thank you. Okay, cool. So now let's do a couple of problems. We're almost done. These are challenge problems. Let's just see how we do with these. Take a look at the circle below. The central angle is measured using radians. Write a proportion that relates the central angle to the length of the arc. So remember how we used to do this? We used to say, okay, the angle over 360 equals the length of the arc over 2 pi r. We're very used to this by now. Classic proportion, nothing new. Well, now if I'm talking about radians, it's not gonna be pi over 360. What is it gonna be? How many radians is 360 degrees? 6.28, but how do we write that? Two pi. So it's theta over 2 pi now. Since I'm measuring it using radians, okay, instead of degrees. And then this is going to be equal to the length of the arc over the circumference. What's the circumference? Two pi r. So what did I just do? Let me just break that down in case anyone would like that. This is just going back to those proportions we've done a bunch of times now. So the angle over a full circle is equal to the arc length over the circumference. Nothing new. The only difference is that since I'm using radians, the whole circle is 2 pi, not 360 anymore. But that kind of does something interesting. Let's see what happens when we cross multiply and when we solve for pi. So cross multiplying, I get 2 pi r theta equals 2 pi s. If I'm solving for theta, what should I do on both sides? Divide by 2 pi r. Well, what happens? What happens on the right side? Yeah, 2 pi cancels out. So theta in radians, theta is equal to s over r, which I think Perla said like a while ago, actually. So that was cool. You actually said that like 5 slides ago, but you didn't really know what you were talking about yet. The measure of the angle, if you want to measure it using radians, the measure of the angle would be the length of the segment divided by the radius. And yes, in that first example, it was 1 radian because the segment was 4 and the radius was also 4. So 4 over 4 gives you 1 radian. So this is actually a really, really useful little trick that you can use in radians, only using radians. Okay? Questions on that? All right. Running kind of low on time, but let's do this one. Yeah, let's do this. So here's an example. We want to know the measure of the angle. Remember what we just said. Theta would be equal to s over r. So all we got to do is fill in the blanks. What's the length of my segment? Or not my segment, my arc length. 2, that's a pi actually, so 2 pi. It's okay. And the radius is how much? 10. So in radians, this would be 1/5 pi, or pi over 5 radians. So that would be answer choice C. Now, let's say I want to convert that to degrees. I want to know how many degrees that is. What do I do to that number? Times what? Which one is it? The other way, 180 over pi. Well, pi over 5 times 180 over pi, what happens? Nope, we're straight across, straight across, straight across. 180 pi over 5 pi. My pi's cancel out. What am I left with? What's 180 divided by 5? $63, 36, 36. So it's 36 degrees. Oops. So kind of interesting, right? Once you get the radian degrees, you can always turn it into degrees. So that's the relationship. And that kind of covers everything. I mean, I did have more questions here, but we can do those when we review on Monday. Yeah, we can do these on Monday. You don't really need to do these for your quiz. Okay, so yes, there is a quiz and a homework. Both are going to be due on Sunday, okay, since we're kind of out of time. So I will post the quiz a little bit on Teams. That plus the homework due Sunday at midnight. Make sure, guys, we learned a lot this week. It was kind of a lot, and I completely agree. So because of that, definitely spend some time, if you can, study before you try to do your quiz. Watch the videos one more time, just make sure you kind of feel good about everything, and then try the quiz. But you have till Sunday night, and if you can't get it done by Sunday night, let me know. As usual, I will definitely give you an extension, but you have to let me know. All right, any final questions before we go? All right, guys, that is all for today. I am sorry for the confusion, but I hope that you guys have a nice rest of your day and a very lovely weekend. I will see you all on Monday. Bye, everyone.
Bye, Miss.
Bye.
I have a question.
What's your question?
No stay.
Can you stay? No, you gotta go. I have algebra next. Bye.